You know, if you've ever been to an ER or even just a regular clinic, you've probably been positioned against one of those cold, solid pieces of plastic.
Oh, yeah, the classic X-ray board.
Exactly. And the technologist steps behind that heavy lead-lined wall. You hear that loud mechanical buzz, and in like a fraction of a second, this completely invisible burst of energy just passes right through your body.
Right, and it's completely painless. You don't feel a thing.
Yeah, you don't feel it at all. But that solid piece of plastic behind you, it somehow instantly catches that invisible energy and just it spits out this perfectly clear, super high resolution digital map of your internal anatomy.
It is honestly a modern miracle when you really break down what's happening.
It really is. I mean, we're looking at a process that happens, what, thousands of times a day in clinics all over the world. But if you actually stop to consider the mechanics of a flat panel digital radiography detector, which is what that board actually is, the physical reality of what's happening inside that plastic shell is just incredibly complex.
Oh, absolutely. It's this incredibly dense convergence of quantum physics, material science, and microelectronics.
Yeah.
And the deeper you look at the engineering required to just pull an image out of thin air, basically, the more you realize that capturing X-ray is really just an exercise in highly controlled energy conversion.
And that conversion process is exactly what we are going to dissect today. Welcome to the deep dive. Today we're operating off some really fascinating notes and microscopic visual diagrams from a presentation on digital radiography. Specifically, it's Chapter 22, RA122.
Right. The real foundational textbook stuff.
Yeah, but we're going to make it totally accessible. You don't need a medical degree to understand this. Our mission here is to just demystify the internal architecture of these digital radiography panels. How do they actually catch that energy? And to start, our source material establishes this really strict divide in how these panels are actually manufactured.
Yes, there are two overarching classes of digital detectors. You have direct conversion and you have indirect conversion. And the terminology there is very literal. The distinction lies entirely in the physical pathway that the X-ray photon takes to actually become an electrical charge.
Okay, let's unpack this, because I've been looking at the diagrams for both of these, and my instinct is to compare this to, well, to translating a language.
Oh, I like that. How so?
Well, so the direct conversion panel operates somewhat like a truly bilingual person, right? They hear a sentence in Spanish, and they instantly directly translate it to English in their head. It's a single-phase interaction. An invisible X-ray photon hits the material, and it instantly drops out an electron.
Right. Direct and immediate.
Exactly. But then the indirect conversion panel, that acts more like using a middleman or like an interpreter. It takes the X-ray energy, converts it into a flash of visible light first, like translating the Spanish into, say, French first, and then it uses a totally separate sensor layer to turn that light into electricity.
That is actually a brilliant analogy. The middleman concept perfectly describes the indirect conversion method. So let's look at the actual science behind your interpreter layer.
Yeah, what is actually doing the translating there?
So the physical layer responsible for creating that intermediate flash of visible light is called a scintillator.
A scintillator.
Right. When X-ray photons strike the scintillator, the material absorbs that high-energy radiation and it emits visible light. But here's the catching ante. A computer processor cannot read photons of light. It needs an electrical current to make data.
So it needs the second part of the translation.
Exactly. So laminated directly beneath that scintillator is a photodiode layer. And this is composed of amorphous silicon, which you'll usually see denoted in the text as ASIH.
Okay, I actually want to pause on that word amorphous, because the text uses it heavily for both the direct and the indirect panels. Amorphous silicon, amorphous selenium.
Yes, it's a critical concept.
Right, but if we were building this highly precise, multi-million-dollar medical equipment, why are we using amorphous materials? Like, shouldn't we be using a highly structured, perfect crystal lattice or something?
Well, it all comes down to how electrons travel. Amorphous simply means that the material lacks a defined, repeating crystalline structure. It's non-crystalline.
Okay.
If you used a traditional polycrystalline semiconductor, the material would be full of these tiny grain boundaries, basically microscopic fault lines where the different crystals meet up against each other.
Like cracks in a pavement.
Exactly like cracks in a paper.
Yeah.
And when an electron tries to travel through that material, it hits one of those boundaries and it scatters. And that scattering ultimately blurs the final electrical signal.
Oh, wow. So you lose the sharpness of the image before the computer even sees it.
Precisely. By depositing the silicon or the selenium in an amorphous state, the manufacturers create this completely uniform, continuous layer, so the electrical charge can travel directly downward to the sensor without being deflected by any of those microscopic structural boundaries.
That makes so much sense. So the amorphous silicon layer acts as the second phase of the indirect panel. It catches the visible light from the scintillator and turns it into an electric charge.
You've got it.
Okay, so contrast that with the direct conversion method, because the text notes that direct panels completely eliminate the scintillator layer entirely. There is no flash of visible light, no middleman.
Right. Instead of a scintillator, they use a thick layer of amorphous selenium, or a C.
And how does that skip the light phase?
Because amorphous selenium is what we call a photoconductor. When the X-ray photons interact directly with the selenium atoms, the ionizing energy of the X-ray physically frees electrons right out of the selenium.
Just immediately knocks them loose.
Exactly. And before those electrons can sort of snap back and recombine, a high-voltage electrical field that's being applied across the panel instantly pulls those freed electrons straight down to the collection grid. It bypasses the visible light spectrum entirely.
Wait. If the direct conversion method turns an X-ray straight into a signal without the middleman light step, why wouldn't every single manufacturer just use that method?
That is the golden question.
Right, like introducing a scintillator to create a flash of light just seems like you're adding an opportunity for the light to scatter and make the image blurry.
You are absolutely right. And what you're identifying there is the core engineering trade-off in all of radiography.
Oh, okay.
Yes, direct conversion using amorphous selenium gives you exceptional spatial resolution, precisely because there is no light scatter. It is fantastic for procedures like mammography, where seeing microscopic detail is literally a matter of life and death.
Okay, so what's the downside?
The downside is that amorphous selenium is not as efficient at absorbing higher energy X-rays compared to the scintillators. To get a good signal for a really thick body part, like a lateral chest X-ray.
Where the beam has to go through a lot of dense tissue and bone.
Exactly. To capture that cleanly with direct conversion, you either need a highly unmanageable, incredibly thick layer of selenium in the panel, or you have to hit the patient with a much higher dose of radiation.
Ah, I see. And the fundamental rule of radiography, which the text highlights, is L-OR, as low as reasonably achievable.
L-era, exactly. You never, ever increase patient dose if you don't have to.
Right.
So that's where indirect panels shine. The scintillator materials are incredibly dense. They absorb X-rays highly efficiently. A single X-ray photon hitting a scintillator can produce thousands of visible light photons.
Oh, wow. So it acts like an amplifier.
It's exactly an amplifier. It takes a tiny signal and boosts it, allowing you to capture a diagnostic image using far less radiation on the patient. But the trade-off, as you pointed out earlier, is you now have to figure out how to control the scatter of all that resulting light.
Which brings us to section 2 of our notes and the actual materials used for these interpreter scintillators, because there are microscopic images in the text of the two primary scintillator materials used in indirect panels. And visually, they are wild. They look nothing alike.
No, they are structurally completely distinct, and their shapes absolutely dictate how they handle that burst of light.
Yeah, so for everyone listening, the first one is gadolinium oxysulfide GD2O2S. And under a microscope, it basically just looks like packed gravel. It's a powder.
Right, a granular layer.
But then the second material, cesium iodide, or CSI, it looks like a dense forest of vertical bamboo. It's composed of these tiny microscopic crystalline needles pointing straight up. So my question is, if both of these materials serve the exact same function, absorbing an X-ray to make a flash of light, why does the physical shape matter so much?
What's fascinating here is how shape impacts the geometry of light. Let's take the gravel first. When an X-ray photon strikes that gadolinium powder, the resulting flash of light is isotropic.
Isotropic, meaning it scatters outward in all directions equally, like a little starburst.
Exactly like a starburst. Because it's a granular powder, the light just bounces off all the surrounding grains and it spreads out laterally.
Okay.
Now remember that this light still has to travel all the way down to the amorphous silicon sensor at the bottom of the panel.
Right.
If the light spreads out widely on its way down, a single X-ray strike at the top ends up activating a huge cluster of pixels at the bottom, instead of just the one pixel right underneath it.
Ah, so the signal bleeds.
It bleeds. And this lateral spread inherently lowers the spatial resolution of the final image. It makes it slightly fuzzier.
I see the physics there. But that just raises another question for me. If the gadolinium powder degrades the sharpness through that isotropic scatter, Why do manufacturers use it at all? Why not just use the bamboo needles for everything?
Ruggedness, primarily, and manufacturing cost. Gadolinium powder is incredibly durable. Historically, it was heavily utilized in those older portable cassette systems where the equipment was constantly being banged around the hospital.
Makes sense. You can't really break a powder.
Exactly. But as engineering progressed, if you wanted to push for higher resolution without sacrificing that great dose efficiency, you had to engineer the cesium iodide needles,
The bamboo forest.
the bamboo forest.
Yeah.
Because cesium iodide is literally grown into these microscopic vertical crystalline needles, it completely changes the behavior of the emitted light. When an X-ray strikes the top of one of those needles, the light doesn't scatter isotropically. The crystalline boundary of the needle forces the light to act through total internal reflection.
Wait, like a fiber optic cable.
It functions exactly like a natural microscopic fiber optic tube. The light is forced to just bounce straight down the internal shaft of the needle directly to the specific photodiode waiting at the bottom.
Oh, that is brilliant.
Isn't it? By heavily restricting that lateral spread, the cesium iodide preserves the original sharp profile of the X-ray beam. So you get the high dose efficiency of an indirect panel, but with a sharpness that rivals the direct selenium panels.
That is just a staggering piece of microengineering to grow crystals that act like millions of tiny fiber optic wires.
Yeah,
Incredible. But okay, let's move down a layer in the panel.
let's do it.
Regardless of whether we are using the direct method or the indirect method, the panel has now successfully converted the X-ray event into a localized electrical charge, right? But that charge is just essentially trapped sitting in the panel. How does the machine actually read it and organize it into a digital canvas we can look at?
Well, the text details two primary readout architectures for these panels.
Yeah.
You have CCDs, which are charge-coupled devices, and you have TFTs, which stands for thin film transistors.
Okay, I know CCDs are used in like standard digital cameras.
Exactly. They're kind of a legacy technology in this field. They pass the electrical charges down the sensor like a bucket brigade.
Yeah.
But modern, large-format medical radiography panels predominantly rely on the TFT active matrix array.
Okay, let's focus on the TFT array then, because the diagrams show this as a massive microscopic grid spread across the entire panel. It honestly looks like a high-density spreadsheet.
That is the perfect mental model. The TFT array is divided into thousands, sometimes literally millions, of individual microscopic squares called DELs. DEL, detector element.
DELs, got it.
And each DEL roughly corresponds to a single pixel in the final image.
Okay, here's where it gets really interesting in the source material, because I sort of assumed a detector element was just a solid patch of sensing material, just a 100% active square. But the diagram of a single DEL shows that it's divided up, it's zoned.
Yes, it is very crowded inside that tiny square.
Right. There's the active sensing area, sure, but there are also all these physical components stuffed inside it. There's a storage capacitor, there's a microscopic gate switch, there are data lines running through it, and the text actually refers to these components as dead zones.
Because they are dead zones. Those specific areas of the DEL cannot sense X-rays or light. They are pure electronic plumbing.
But wait, if you're trying to capture every single photon possible to keep the patient's radiation dose as low as you can, why would you tolerate dead zones? Why not build a panel that is 100% active sensing material?
Because the electrical charge needs somewhere to go, and it has to be controlled. Once the amorphous layer generates those electrons, they have to be held in place temporarily.
Ah, so that's what the capacitor is doing.
Exactly. That requires a physical storage capacitor inside every single DEL. Furthermore, the computer needs to read the panel systematically, row by column. It can't just read the whole board at once, or it would just be a chaotic surge of static electricity.
Right.
So every DEL requires a thin film transistor, a physical microscopic switch. A signal opens the transistor, which allows the stored electrons in the capacitor to flow down a tiny data wire to the amplifier. Capacitors, transistors, and wires are physical objects. They take up real estate.
And you just cannot overlap the plumbing with the sensor.
You cannot, which introduces a vitally important mathematical ratio in radiology known as the fill factor.
Fill factor.
Yes. The fill factor is simply the percentage of the DEL's total area that is dedicated solely to the active sensing material.
Okay, so if a DEL allocates, say, 20% of its microscopic square to the capacitor and the transistor switch, then it has an 80% fill factor.
You got it perfectly. And this is not just a piece of trivia. Fill factor directly dictates clinical outcomes for the patient.
How?
Because a high fill factor means the panel has a really large active area to catch the incoming signal. This translates directly to high X-ray dose efficiency. The detector catches more data with less radiation, allowing the technologist to use a lower exposure technique.
But wait, let's test that idea against the push for higher resolution.
Okay, go ahead.
Because in the display world, right, like with TVs, if you want a sharper TV, you make the pixels smaller so you can pack way more of them into the screen.
Right, a 4K TV versus a 1080p TV.
Exactly. So if a manufacturer wants to build a higher resolution X-ray panel, they would just need to shrink the size of the DELs, right? Pack more in.
And that is exactly where the physics trap lies.
Oh.
Yeah. If you shrink the total size of the microscopic DEL, you would naturally think you get a sharper image. But the electronic plumbing, that transistor and the capacitor, they cannot be shrunk past a certain physical threshold. We just don't have the technology to make them infinitely small.
Oh, wow. I see it. So if the square gets smaller, but the transistor has to stay the exact same size, the dead zone starts eating up a much larger percentage of the DEL.
Exactly. Shrinking the pixel size inherently reduces your fill factor. Your 80% fill factor might suddenly drop to a 60% fill factor.
And now your panel is actively ignoring 40% of the information hitting it.
Which is terrible, because to compensate for that severe drop in signal, the technologist would have to dramatically increase the radiation dose to the patient just to push enough photons into that tiny shrinking active area to get a usable picture.
Wow.
So while engineers are constantly trying to improve spatial resolution, they are fundamentally bound by the physical limits of the thin film transistor's fill factor. It's a constant balancing act.
That is just a brilliant explanation of the compromise they have to make. You can't just infinitely shrink pixels without penalizing the patient.
No, you really can't.
Well, setting aside the microscopic architecture for a moment, the source material also details the mechanical operation of these panels in a real clinical setting. Specifically, it talks about the evolution of wireless portable panels.
Oh, yes. A total game changer for technologists.
Because in a trauma scenario, a tech will slide a flat panel beneath a patient in a bed, and then they'll fire a portable X-ray generator from, like, across the room.
Which is amazing because it eliminates all those heavy tethered cables that used to completely limit technologists in a crowded emergency room.
Right, it gets rid of the cables. But reading through the notes, I realized it creates a massive synchronization problem.
It really does.
Because if a wireless panel has absolutely no cord, meaning it's not plugged into the computer that actually triggers the X-ray tube to fire, how does the TFT array inside the panel know when to start capturing data?
Ah, yes. If we connect this to the bigger picture, that is the auto-detection problem. Historically, you're right, the panel and the generator had to talk to each other via a cord. The generator would basically send a signal saying, hey, I am about to fire, open your gates and get ready.
Right, a closed communication loop. But if the panel is completely untethered, how does it know the X-ray is happening? It's just sitting there in the dark.
Well, it utilizes the radiation itself as the trigger.
No, wait, really?
Yes, through a technology called auto-detection. Prior to the technologist firing the beam, the wireless panel's internal battery pre-charges the entire TFT array. Every single capacitor in that grid is loaded with a baseline voltage. So the panel just sits in this highly sensitive prime state.
It's essentially holding tension, like a mousetrap waiting for a disruption.
That's a great way to put it. When the technologist hits the button and triggers the exposure, the X-ray beam passes through the patient and strikes the panel. The ionizing radiation hits the scintillator, or the photoconductor, creating that cascade of electrons we talked about earlier. The sudden presence of all those free electrons instantly drops the electrical resistance across the entire semiconductor layer.
And because the resistance drops, that baseline voltage that was just sitting in the TFT array suddenly spikes or shifts.
Yes. The panel constantly monitors for that sudden voltage shift at the physical edges of the array. The panel's internal brain, its logic controller, recognizes that shift not as an electrical error, but as the physical footprint of an X-ray exposure beginning.
Oh, wow.
So the actual physical strike of the radiation acts as the mechanical switch. It transitions the panel from a primed state into an active integration state, where it immediately begins hoarding the electrical charge in all those little capacitors to build the image.
That is incredibly elegant. It doesn't need to be told the beam is firing because the beam physically forces the door open.
Exactly.
But okay, that addresses the capture. What about the readout? How does it know the exposure is finished so it could actually send the image back to the computer?
It just monitors that same voltage state in reverse.
Oh, I see.
Yeah. The exposure is terminated either manually by the technologist letting go of the trigger, or through an automatic exposure control, an AEC system, that cuts the beam automatically when enough radiation has reached the panel.
Right.
The moment the X-ray beam stops, the production of electrons in the amorphous layer instantly ceases. The resistance stabilizes back to normal. The panel detects the end of that voltage shift, and it immediately closes the active integration phase and triggers the readout phase.
Where it goes row by row, opening all those little TFT gates we talked about and dumping the stored charge down the data lines.
Exactly. The image data is transmitted wirelessly over Wi-Fi to the tech's console, and then automatically the panel initiates a scrub cycle. It discharges any residual ghost charges left in the grid, resets that baseline voltage, and is immediately ready for the next exposure. It is a fully autonomous, self-contained loop.
Unbelievable. Which actually brings us to a really harsh reality outlined in Section 5 of our text.
Oh, the handling warnings.
Yeah. So what does this all mean for the people using them? Because we've spent this whole time breaking down amorphous photoconductors, microscopic fiber optic needle arrays, dead zones, fill factors, autonomous voltage triggers. I mean, it is a highly tuned, deeply complex ecosystem of microelectronics.
It is essentially a supercomputer inside a plastic tray.
Exactly. And yet, this incredible technology is deployed in literally the most chaotic environment possible, a hospital emergency room.
Yes, the clinical environment is the exact opposite of the perfectly sterile, vibration-free, clean rooms where these TFT substrates are actually manufactured.
And the source material heavily lists the real-world precautions for handling these flat panel detectors. They highlight fluid invasion like blood or cleaning chemicals, weight load restrictions, and bending. And the text emphasizes multiple times the absolutely catastrophic nature of dropping the panel. It reads less like a standard user manual and more like a dire warning.
Well, if you apply everything we've analyzed today about the internal structure, those warnings are entirely justified, because the extreme fragility of these panels is directly tied to the physics that make them work in the first place.
So let's break down that physical damage. If a technologist actually drops a wireless panel on a hard hospital floor, what is actually breaking inside? Because from the outside, it might just look like a scuffed carbon fiber shell.
The external shell is ruggedized, sure, but the internal TFT active matrix array, that microscopic spreadsheet, is typically printed on a highly rigid, very thin glass substrate.
Glass.
Yes, glass. So if a panel suffers a sharp impact from a drop, that microscopic glass substrate inside can fracture. And if you fracture the substrate, you physically sever the microscopic gate lines and data wires running between all those detector elements.
Oh, wow. Which means the electrical charge trapped in the capacitors literally has no physical pathway to reach the amplifier. It's just stranded.
Exactly. A severed data line results in an entire column of pixels going completely dead on the final image. A severed gate line means an entire row cannot be triggered at all. You don't just get a blurry spot. You lose critical diagnostic data. It just shows up as a bright white or pitch black line on the X-ray.
That is terrifying in a trauma situation. What about the weight load restrictions? The text warns heavily about bending the panel. Like, what if a heavy patient is unevenly positioned on top of it in a soft, squishy hospital bed?
Bending introduces a completely different type of catastrophic failure, particularly if we're talking about an indirect panel utilizing cesium iodide.
Oh, right, the bamboo forest of fiber optic needles.
Right. Think about those needles. They are grown perfectly perpendicularly to the substrate. They rely entirely on their perfect vertical alignment to bounce the light straight down via total internal reflection.
Yeah.
If you put hundreds of pounds of uneven torque on the panel, the whole board flexes. And when it flexes, those brittle, microscopic crystalline needles just shear and snap in half.
Oh, that makes total sense. If the needle breaks, the fiber optic channel is ruined.
The light is no longer contained. It leaks out at the microscopic fracture point and scatters isotropically into the surrounding tissue of the scintillator. This creates permanent artifacts on the detector. Basically, areas where the image will always be hazy or distorted on every future X-ray, because the physical architecture channeling the light has been crushed.
Wow. And the text explicitly notes that these aren't issues a hospital's biomedical tech can just patch up with some solder. If a panel suffers a drop or a severe flex that damages the TFT array or those crystals, the unit has to be completely pulled from service and sent back to the manufacturer for analysis.
You cannot solder a microscopic thin film transistor gate back together in a hospital basement. Once the structural integrity of the microelectronics is compromised, the diagnostic validity of the panel is compromised. A hospital simply cannot risk a misdiagnosis because a fractured panel artificially created what looks like a shadow on a patient's chest X-ray.
It is such a profound dichotomy. the most vital diagnostic tool in the trauma bay, capable of capturing invisible energy at a quantum level, can be completely undone by an uneven mattress or just a slippery pair of gloves. It forces a tremendous amount of discipline on the professionals handling them.
It really does. The extreme precision of the engineering demands extreme precision in handling. There's no getting around it.
Well, we have mapped out a massive technological journey today from our source material. We started with an invisible X-ray photon striking an amorphous photoconductor or a highly structured scintillator. We evaluated the critical importance of a non-crystalline transit path, and we broke down how total internal reflection preserves spatial resolution.
We really covered a lot of ground.
We did. We examined the physical trade-offs inside a single detector element, where the necessity of transistors battles against the fill factor and dose efficiency. And we looked at how changes in semiconductor resistance allow for untethered auto-detection, all while operating inside this incredibly fragile glass substrate ecosystem.
When you look at the entire chain of events from start to finish, it fundamentally changes how you view medical imaging. It's not just taking a picture. It is the real-time mapping of high-energy physics.
It really is. And looking at how perfectly we have engineered these active matrix arrays to catch this specific wavelength of radiation, it leaves a lingering question for you to think about.
Oh.
Yeah. If we can build an autonomous, self-contained grid that instantly translates invisible, harmful radiation into a flawless digital map just by the physical trigger of the beam hitting it, what other invisible energies are cascading through our environment right now?
That is a fascinating thought.
Right. Energies we pass through every single day, entirely unaware that we could passively map and understand if only we knew how to engineer the right kind of microscopic architecture to catch them.
We just need a completely different type of scintillator for a completely different spectrum of reality.
Exactly. Something to think about the next time you hear that mechanical buzz behind the wall. Thank you for joining us on this deep dive into the architecture of radiography. We'll be back next time with another stack of sources.